In an era where sustainability has become a core priority, the forest is far more than a resource. It is a living ecosystem managed with precision and responsibility. These trees, harvested from certified PIFA or FSC forests, are extracted under strict cycles that ensure continuous renewal. This is where the journey of wood begins, the essential raw material for modern construction and interior design. Every day, convoys deliver freshly cut logs, known as grooms in French, to industrial sawmills, and their destination, advanced facilities, where precision technology and efficiency convert raw material into finished products, such as boards, joists, roof battens, furring strips, strapping, and veneer sheets. Upon arrival, logs are immediately processed. A preliminary visual and automated inspection assesses overall condition, bark coverage, approximate diameter, sweep, or obvious defects. This initial sorting prevents unsuitable material from entering the production line. Advanced technology now takes over. Three-dimensional laser scanners measure each log to within millimeters. These precise data feed optimization software that determines the ideal orientation and cutting pattern. Solid lumber for boards and joists, or premium peeler blocks reserved for high-grade veneer production. Final sorting occurs automatically. Logs are classified by species: pine, spruce, Douglas fir for structural lumber, oak, or beech for premium veneer, and by quality grade. This organized classification maximizes yield and minimizes waste, embodying the principles of circular economy in the modern wood industry. This concludes the first stage of the journey. From forest to factory, logs have been received, measured, and sorted with unmatched accuracy. Next, they will shed their protective bark to expose the valuable timber within. In the following episode, Debarking, the essential first physical transformation. Following the precise sorting performed at reception, the logs now enter the first stage of physical transformation. Debarking is an indispensable step. It removes the protective outer bark to expose the valuable timber, prevent parasitic infestations, and ensure optimal quality during subsequent sawing. In a modern mill, this operation combines mechanical efficiency with full residue valorization. While natural, bark often harbors insects, fungi, and spores that can degrade the timber once sawn. Removing it also prevents unwanted inclusions in final products such as boards, joists, or roof battens. Furthermore, from a circular economy perspective, every fragment of bark is collected and converted into a useful resource. Contemporary mills primarily employ two technologies: mechanical friction debarking and high-pressure hydraulic debarking. The first uses rotating drums fitted with spikes or knives that abrade and peel the bark through friction, while the second projects ultra-high-pressure water jets to detach the bark without aggressive mechanical contact. Here is the core of the mechanical process. The log is driven by powered rollers that rotate it on its axis. Fixed knives or spikes apply controlled pressure, stripping the bark layer by layer. This highly automated system processes multiple logs per minute with remarkable precision, minimizing damage to the underlying wood. Some lines incorporate high-pressure water debarking, especially suited to delicate species or irregular logs. The concentrated jet penetrates beneath the bark and lifts it cleanly without mechanical abrasion. This gentler method produces less fiber loss, but requires careful water recycling management. Nothing is wasted. Bark chips and fragments are immediately conveyed or vacuumed to valorization systems. They fuel biomass boilers that supply a significant portion of the thermal energy required for later drying or mill operations, demonstrating a strong commitment to near-zero waste production. Debarking thus converts raw material into usable timber while integrating sustainability and energy efficiency. In the next episode, These clean logs will enter the decisive phase of primary sawing, where the first boards and cants are born. With the protective bark removed, the clean log, now called a cant or peeler block in some contexts, enters the central phase of transformation, primary sawing. This is where the round natural form begins to become the rectangular pieces we recognize. Wide boards, thick cants for future joists, and rough material destined for roof battens, furring strips, or strapping. In a modern mill, this stage combines raw mechanical power with sophisticated digital optimization to maximize yield and quality. The log is automatically gripped and aligned. Laser sensors and 3D cameras, using data from the initial reception scan, orient the log to best exploit its shape, sweep, taper, and natural defects. This intelligent positioning is the foundation for the highest possible recovery of usable lumber. At the heart of primary sawing lies the head rig, typically a large vertical bandsaw or a double band setup. Guided by lasers and controlled by CNC systems, it makes the initial longitudinal passes, converting the round log into one or more squared cants. The blade, wide and precisely sharpened, cuts with millimeter accuracy, minimizing kerf loss and preserving maximum board footage. The resulting cants are then further subdivided according to the pre-calculated cutting pattern. Advanced optimization software evaluates hundreds of possible layouts in seconds, factoring in target dimensions for boards, joists, or future resawing into roof battens, and furring strips, and selects the pattern that delivers the highest volume of high-grade lumber while respecting quality constraints. This digital decision-making significantly outperforms traditional manual or fixed pattern sawing. Every cut generates byproducts: fine sawdust, slabs, and edgings. These are instantly collected via powerful aspiration systems and dedicated conveyors. Sawdust often feeds panel manufacturing lines or pellet production, while larger offcuts supply biomass energy systems that power parts of the mill. This integrated handling contributes to near total resource utilization. At the end of primary sawing, the rough lumber-thick boards, cants destined for joists, bases for roof battens, moves forward, still green and oversized but already in usable geometric form, ready for secondary processing and stabilization. Primary sawing marks the decisive transition from natural round form to engineered rectangular geometry. In the next episode, these rough pieces will be refined through secondary sawing and resawing to achieve the exact dimensions required for roof battens, furring strips, and strapping. The pieces produced by primary sawing cants, thick boards, and rough blanks already possess their basic rectangular shape, yet their dimensions remain too generous for most final applications. Secondary sawing and resawing now refine these elements. They reduce widths and thicknesses to exact specifications and prepare the specialized products such as roof battens, furring strips, and strapping. This phase bridges the gap between rough lumber and dimensionally accurate components ready for drying and finishing. Rough pieces from primary breakdown are automatically oriented and positioned. Laser sensors remeasure actual dimensions post-primary cut and adjust cutting parameters in real time. This dedicated secondary line employs finer, faster equipment than the head rig, designed for multiple precise passes. The flagship machine of this stage is the multi-blade resaw, fitted with several parallel circular blades set at precise intervals. In one continuous pass, it divides the cant into thin roof battens 12-22 mm thick, rectangular furring strips 18-40 mm 35-60 mm, or near square strapping 20-40 mm 20-40 mm. CNC-guided blades ensure dimensional accuracy within a millimeter critical for structural, cladding, or fastening applications. Artificial intelligence and optimization algorithms play a decisive role here. Overhead optical scanners detect natural defects, knots, checks, color variations, and the system proposes resaw patterns that maximize the volume of high-grade material while minimizing waste. This adaptive approach can increase recovery by 10 to 20% compared to fixed or manual sawing methods. Immediately after cutting, an automated sorting system separates the output roof battens for sheathing support, furring strips for lathing and cladding, strapping for interior framing or shelving. Pieces with minor defects are diverted to byproduct streams, chips, or pellets, while conforming material proceeds toward drying. Secondary sawing and resawing refine intermediate stock into precise, application-ready components. In the next episode, we explore a parallel yet distinct pathway: the production of veneer sheets through peeling and slicing, dedicated to decorative and overlay uses. Parallel to the production of solid structural and dimensional lumber runs a distinct pathway dedicated to decorative and surfacing applications: the manufacture of veneer sheets. These thin slices of wood, ranging in thickness from 0.3 to 3 millimeters, preserve the natural figure, color, and grain of premium species. In a modern facility, veneer production employs precision peeling or slicing techniques that transform select logs into continuous ribbons or individual leaves intended for overlaying panels, furniture, cabinetry, and doors. Only logs of exceptional quality, free of major defects and displaying pronounced, attractive grain, are allocated to veneer production. These peeler blocks frequently undergo preconditioning in steam chambers or hot water vats to soften the fibers, reduce checking during cutting, and enhance the natural beauty of the wood. Rotary peeling remains the most widely used technique for volume production. The log spins at high speed against a stationary razor-sharp horizontal knife that peels away a continuous sheet, much like unrolling paper from a roll. Computer-controlled pressure and angle adjustments maintain consistent thickness across the entire block, even as diameter decreases. This method yields broad, economical sheets ideal for plywood cores, panel overlays, and large-scale furniture components. For the most prestigious and visually striking veneers, quarter-sawn, rift-cut, or book-matched patterns, slicing is preferred. The log, often pre-sawn into flitches, is mounted vertically and sliced by a descending knife, revealing symmetrical grain figures highly valued in fine cabinet making and architectural paneling. Though slower, this method maximizes the aesthetic potential of species, such as walnut burl, maple quilt, or rosewood. Freshly cut veneer is extremely thin and moisture-sensitive. It undergoes immediate drying in belt or jet dryers to reach a stable moisture content of 81%. Optical scanners and train graders then sort the dried sheets by face, quality, grain continuity, and absence of defects. Premium faces are reserved for visible surfaces, while lower-grade material finds use in core layers or secondary applications. Veneer production exemplifies a refined transformation of wood, preserving and enhancing its natural beauty for high-value decorative purposes. In the next episode, we return to the full range of products, solid lumber and veneer alike, for the critical stabilization stage, controlled drying. Parallel to the production of solid structural and dimensional lumber runs a distinct pathway dedicated to decorative and surfacing applications: the manufacture of veneer sheets. These thin slices of wood, ranging in thickness from 0.3 to 3 millimeters, preserve the natural figure, color, and grain of premium species. In a modern facility, veneer production employs precision peeling or slicing techniques that transform select logs into continuous ribbons or individual leaves intended for overlaying panels, furniture, cabinetry, and doors. Rotary peeling remains the most widely used technique for volume production. The log spins at high speed against a stationary, razor-sharp horizontal knife that peels away a continuous sheet, much like unrolling paper from a roll. Computer-controlled pressure and angle adjustments maintain consistent thickness across the entire block, even as diameter decreases. This method yields broad, economical sheets ideal for plywood cores, panel overlays, and large-scale furniture components. For the most prestigious and visually striking veneers, quarter-sawn, rift-cut, or book-matched patterns, slicing is preferred. The log, often pre-sawn into flitches, is mounted vertically and sliced by a descending knife, revealing symmetrical grain, figures highly valued in fine cabinet making and architectural paneling. Though slower, this method maximizes the aesthetic potential of species such as walnut burl, maple quilt, or rosewood. Freshly cut veneer is extremely thin and moisture sensitive. It undergoes immediate drying in belt or jet dryers to reach a stable moisture content of 81%. Optical scanners and trained graders then sort the dried sheets by faced, dot, quality, grain, continuity, and absence of defects. Premium faces are reserved for visible surfaces, while lower-grade material finds use in core layers or secondary applications. Veneer production exemplifies a refined transformation of wood, preserving and enhancing its natural beauty for high-value decorative purposes. In the next episode, we return to the full range of products, solid lumber and veneer alike, for the critical stabilization stage, controlled drying. Having reached stable moisture content through controlled drying, the products now possess the necessary rigidity and dimensional predictability. However, surfaces remain rough from sawing, dimensions may still carry minor tolerances, and unprotected wood remains vulnerable to biological and environmental degradation. Surfacing, profiling, and protective treatments form the concluding phase of value-adding. They deliver exact dimensional accuracy, functional or aesthetic profiles, and long-term durability, transforming dried stock into ready-to-use or ready-to-assemble components. Surfacing removes the final saw marks and irregularities left after drying. Modern four-sided planers or molders dress all faces simultaneously in a single pass. CNC-controlled cutter heads adjust automatically to achieve precise target dimensions. For example, a nominal 2x4 joist or a 1x6 roof batten within tight tolerances. The fine shavings produced are immediately extracted and directed to pellet production or biomass systems. Profiling imparts specialized geometries required for installation or appearance. Multi-spindle CNC molders cut precise profiles, tongue and groove for furring strips, used in paneling, drip edges or chamfers on roof battens, or custom shapes on strapping for framing applications. These machines allow rapid changeover between profiles, enabling the mill to meet diverse customer specifications with consistent accuracy. Depending on intended exposure, interior, exterior above ground, or ground contact, the wood receives appropriate protection. Pressure impregnation forces preservatives deep into the cell structure to guard against insects, fungi, and decay. Thermal modification, a chemical-free process conducted at 180-220-200 C, alters the wood's cellular chemistry to enhance dimensional stability and biological resistance. Surface treatments provide additional water repellency or fire resistance while complying with current environmental and health standards. Before packaging, rigorous final inspection verifies all critical parameters: dimensional compliance, surface quality, profile fidelity, and treatment efficacy. Automated optical and laser systems classify pieces by grade, while human oversight confirms subjective attributes. This multi-layer verification ensures every product meets or exceeds industry standards and customer expectations. Surfacing, profiling, and protective treatments complete the transformation. The wood now possesses exact form, functional capability, and long-term durability. In the final episode, we witness the ultimate validation, quality assurance, packaging, and dispatch, closing the full cycle from forest log to delivered product. Following surfacing, profiling, and protective treatments, the wood products have reached their definitive form, dimensional precision, and protective treatment level. The remaining steps, final quality assurance, secure packaging, and dispatch ensure every board, joist, roof batten, furring strip, strapping piece, and veneer sheet meets rigorous standards, remains undamaged during transit, and arrives ready for immediate use by builders, manufacturers, and craftsmen. Final quality control combines multiple automated technologies. Laser gauges confirm exact length, width, thickness, and squareness to within fractions of a millimeter. High-resolution cameras, supported by machine vision algorithms, detect surface imperfections, color consistency, and profile accuracy. Ultrasonic probes identify any hidden internal defects that may have developed during earlier processing. Non-conforming items are automatically diverted for rework, downgrading, or byproduct utilization. Automated systems are complemented by human expertise for subjective evaluations, grain aesthetics, tactile smoothness, treatment odor, and for random sampling audits. Each accepted lot receives permanent traceability marking, origin of the log, processing dates, drying schedule, treatment type, and test results. This comprehensive documentation supports chain of custody certification, regulatory compliance, and customer confidence. Packaging protects the finished material throughout transportation and storage. Automated lines form consistent unit loads, such as 50 furring strips or 20 treated joists. Then encase them in weather-resistant film to shield against moisture and abrasion. Edge protectors and strapping prevent shifting or damage. Each pallet is labeled with product specifications, quantity, weight, destination, and handling instructions for immediate identification upon arrival. Pallets are loaded with care to maximize stability and transport efficiency. Once dispatched, these products, originating from responsibly managed forests, reach construction sites, manufacturing facilities, distribution centers, and retail outlets across regions and continents. From standing tree to finished component, every stage has been engineered for performance, longevity, and environmental responsibility. This concludes our journey through the modern wood products manufacturing process. From the sustainably managed forest to the delivered finished material, precision technology, resource optimization, and environmental stewardship converge to produce reliable, beautiful, and enduring products. Thank you for joining us on this exploration of how wood continues to serve humanity through advanced industrial craftsmanship.